attention to the case where we had isotropic, non-dispersive media described by dielectric constants and permeability constants, so that we wrote B and epsilon E and B as mu H, and we found that under this with this description of the medium, that we ended up with wave equations for E and H, or equivalently B and D, which looks like the wave equation in vacuum, except now what we have is that we have a dispersion relation which says that omega over k is equal to c over the square root of mu times epsilon. Okay? And this is the phase velocity of a plane wave. And the index of refraction then is determined by the ratio of the speed of light to the phase velocity, is determined by those material constants, familiar relation. So we have plane waves that we discussed, where we wrote E and H in terms of the usual kind of complex amplitude. Where E and H were transverse and satisfy the usual relationships. We have this relationship here, but what we also found was that the magnitude of E and H are not equal, generally speaking, but related by what we call the wave impedance, which was equal to the square root of mu over epsilon. And the energy propagates according to the Poynting vector, which inside the medium is related to E cross H. And what we showed last time was that the intensity propagates in a plane wave at the phase velocity, and the energy density, total energy density, where the total energy density was given by epsilon E squared. Okay, so that's where we were last time. All right, so what we want to talk about today is moving beyond this approximation, where we treated in this discussion, when I write this expression d equals epsilon E, what I'm saying is locally at some space-time point, d is instantaneously related to E through epsilon. And remember that came from, remember D the displacement field was equal to E. So this is not an approximation, this is a definition. Okay, where P is the polarization, it's the electric dipole moment, coarse grain per unit volume. So generally for an isotropic medium where we forget about any of the spatial dependence, but the temporal response is generally determined as we discussed. There will, if we have a linear medium, then the polarization is related linearly which is typically independent of this isotropic through the susceptibility. So this we discussed, we defined as the electric susceptibility. It tells me how susceptible the medium is to being polarized in the presence of some electric field, okay? And generally speaking, the polarization induced at some time t is not instantaneously related to the field at that same time, but there's some response time. So a response function, which is given here, okay? Of course, what that means is in this linear approximation that really, when we talk about the proportionality, we really should be thinking about this in the frequency domain. So for a given frequency, there's a certain amount of polarization that's induced, and that proportionality constant typically will depend on frequency. The strength of how much polarization I induce depends on the frequency with which we're driving those dipoles. And that's particularly true if I'm close to some resonance of the binding of the charges. Okay? Yeah?
The limit in the time integral, the upper limit would have to be t, right? You don't integrate into the future.
That's correct.
So does that complicate the Fourier transform?
No, we'll talk about that. That causality gives rise to the Kramers-Kronig relation, which we'll talk about on Tuesday. That causality is built in. So we'll talk about that next lecture. But it's a good point. Okay. So, right. So what we want to talk about today is some kind of model material properties determine the susceptibility. So in homework, you're looking at an example of this where we're looking at a conductor. We want to talk about, in today's lecture, our dielectrics. Okay? And we have this is not a fundamental quantity, it's something that depends on the specific material at hand. Whether it's the atmosphere, whether we're talking about, a KTP crystal, what have you, whatever that material is, will determine something about the nature of susceptibility. Okay? Now, remember, as we have been discussing, these relations are what we call the macroscopic Maxwell's equations, or macroscopic fields, where we've done this coarse graining over many, many microscopic constituents. So when we talk about the material in response, well, the material is made up of microscopic constituents, and what we would typically do is first we would talk about some kind of microscopic response. So if I want to think about microscopically, I think about some molecule which has some induced electric dipole moment, which is depending on the field that is present. Okay, so the field induces a dipole moment. And again, in the linear approximation, we would say that that's proportional to the field through a proportionality constant that we call alpha, which generally will be a tensor in the same way that we talk generally for the susceptibility would generally be a tensor. And in the same way that we just discussed the same relation about the instantaneous time response versus some kind of delayed time response, this expression is really only makes sense exactly in the frequency domain, where this is the field at the position of the molecule. Okay. And so these are generally complex quantities. And this object is known as the polarizability tensor. So the question, one question you can ask is, how is the susceptibility related to the polarizability? Remember, the susceptibility is some kind of coarse-grained average over many, many molecules. Something like Avogadro's number of them. 10 of that, something like that. Still a whole lot of molecules. Now generally speaking, so when we talk about the relationship here between the polarizability and the field, what we're talking about is whatever the field is, which if I have a macroscopic medium, then if I have all, a whole bunch of dipoles around that are being polarized somehow in the presence of some external field, then the field that's present here is not just the external field, but the field due to all these other dipoles that are near it, which are creating, their own little dipole fields. And these fields are known as local fields. So the amount of ultimate polarization coarse-grained over some macroscopic number of such dipoles will depend, generally speaking, not just on the, in some simple proportionality constant to the local microscopic polarizability because of what are called local field corrections. Now, that's a complicated business. You have to somehow self-consistently determine how everything orients itself in such a way that it responds both to the external field as well as, it's a nonlinear problem, right? And that's complicated, we're not going to do it. Okay, but you can read about that as local field corrections. On the other hand, if I have a very dilute gas, such that local fields are negligible compared to the external fields, so I might have an atomic vapor, okay? And I'm going to put on a laser field on that vapor. I want to see how that laser field propagates through that atomic vapor. If it's sufficiently dilute, then the external field is a much bigger, you know, if I have a density of 10 to the 11th atoms per cubic centimeter, that's mean the distance between them is so big, and the dipole field falls off like 1 over r cubed, I can ignore those local fields. So if I have a dilute gas where I can ignore the local field corrections, then I can write down a very simple relationship for between the susceptibility and the polarizability. Because I just have, if n is the number of molecules or atoms per unit volume, the number density of constituents, then the induced polarization is just this. So they're essentially equal. So that tells me then that the susceptibility tensor is just the density times the microscopic polarizability. Okay? Quick question. What are the units of alpha? Well, what's the units of n? The way I defined it. 1 over volume. Okay? And so, what are the units of chi? Well, P has the same dimensions as E. So what's units of chi? Dimensionless. Okay, I'm sorry, I meant to say this guy is omega. This is dimensionless. So if this is dimensionless, then the units of alpha are units of volume. So if you were to guess what is the polarizability of a hydrogen atom, what would you guess? There's only one length scale in the problem, the Bohr radius. So it's like the Bohr radius cubed. Okay? This is the kind of physical argument you should think about a little bit to develop your intuition about things. One of the reasons I like these units because I can figure that out. And what is it in SI units? Anyone know what the hell a debye is? I don't. So scales are important. All right, enough of that diatribe. Let's get back to the derivation at hand. So our goal then is to derive, based on some model, what the molecular or atomic polarizability is under some model. I mean, you could use a quantum mechanical description. You could use perturbation theory. So you guys worked on perturbation theory in 522 this week or these weeks, right? You could say you have some atomic orbitals and you put on some electric field and they polarize, and you want to know how much. That would give you the atomic polarizability from a quantum mechanical description. We're not going to go there. Well, today we'll talk about a simple and very powerful model, a classical model for dielectric response. Which is called the Lorentz oscillator model. Obviously, Lorentz wrote this down first. very simple. So the idea is to treat the bound charges that make up the microscopic constituents. So the bound charges are treated as harmonic oscillators. Okay, so we're thinking about our bound, say, electron bound, or electrons bound to the nuclei in a molecule. So, I mean, we know sort of quantum mechanically we might have some atomic orbital, maybe it's an s orbital, maybe it's a p orbital, it doesn't really matter. The point is that it's fairly isotropic, there's no dipole moment, there's the nucleus in the middle, the electron is isotropically around it. We put on some, say, electric field, and we get some polarization. In this case, the center of the electron charge moves down, and we have some induced dipole moment. Okay. So this, obviously, this picture here, this is not a tensor polarizable material. We'll just treat a simple case. We'll treat this where we ignore the fact that we might have some dipole moment that's induced in a direction different from the applied field. This is an example of a scalar polarizability. We'll just treat that case here. So the idea then is to just say, well, okay, there's some charge on the spring. In this case, the charge is the electron, and it's a charge on the spring. And there's some equilibrium position, and when it's at that equilibrium position, which would say in the quantum mechanics would correspond to the ground state, there's no dipole moment. Okay? So there's some displacement of this guy from its equilibrium position. And the goal then, so the dipole moment of this single electron bound system minus E times its displacement. So the goal then is to determine how much displacement we get from equilibrium when we apply an external field, and then from that determine what the polarizability is. All right, so that's a trivial mechanics problem. We have harmonic oscillator. We'll say this harmonic oscillator, there's some natural resonance frequency, omega naught, and that there's some damping force that's intrinsic to however the molecule is made up, has some natural line width associated with it. Okay, so omega naught is the resonance frequency. And gamma is what we call the natural line width for reasons that we'll remind you of in a moment. Okay. It doesn't actually have to be the natural line width. It could be due to collisions. Let me just call it the line width. Whatever is giving rise to that damping. Might have collisions between the molecules that would also tend to dephase the oscillator and cause it to decay. Whatever it is, it's got some damping rate. So then we can write down what the equation of motion of this displacement is. So the equation of motion for the displacement of the electron from equilibrium. The acceleration is the force on the particle. We have the Hooke's law, which says that there is a restoring force depending on the natural frequency. Hooke's law. We have damping, which is proportional to the velocity with rate gamma. And then we have the external force, which is the Lorentz force. So this is the electric field at the position of the molecule as a function of time. And then we have, generally speaking, this as well. And as we have mentioned now many times, if we're talking about the response in the presence of an electromagnetic wave, well then E and B are of the same order. And so the relative strength of these forces depends on the strength of the velocity compared to the speed of light. So if we're talking about if our forces are such that the electrons are not moving near relativistic speeds, then we can neglect this. So this is negligible for R dot, much, much less than C when B is on the order of E. Of course, if we had no electric field, well then this would be the dominant effect. But we do have an electric field. Okay, so this is our Lorentz oscillator, and our electric field here is given by the local electric field has some complex amplitude and I'm sorry, it's oscillating at some general frequency. Omega doesn't have to equal omega naught. Whatever frequency it's incident upon. Okay? So now we just have to solve this ODE. And as you know, generally speaking, there's going to be a transient response because of this damping. And eventually, the oscillator will come to steady state. And in steady state, as we've discussed before, the oscillator is driven and will start ultimately, in steady state, oscillate at the frequency of the drive, regardless of what the natural resonance frequency is. And so in steady state, we know what the displacement is. It's got some amplitude, which is generally complex, and it will oscillate at the frequency of the drive. Which is the frequency of oscillation of the wave. So, under that condition, we can just plug in this ansatz where this is treated as our driving field. And we have, so if we have it in the time domain, R double dot plus omega 0 squared plus gamma R dot plus omega 0 squared R is equal to minus E over N dt. In the frequency domain, this becomes, under this assumption, minus omega squared R twiddle minus I omega gamma R twiddle plus omega 0 squared arc-wheel. So every time derivative becomes a multiplication by I omega is equal to minus UNM E02. So we love the Fourier domain because derivatives become multiplication. And we love multiplication. I'm going to get a t-shirt that says that. All right, so, oh, what am I doing? I'm not doing that. I'm doing that. So we can then just quickly solve for our complex amplitude, and we've solved the ODE in steady state. We haven't solved the transient response, but we don't care about that. After a short time it comes to steady state. So we get, this is equal to minus E over n omega 0 squared minus omega squared minus I omega gamma times E0. And thus, this in steady state, we know that the dipole moment will be the induced dipole moment, ignoring local field effects. Well, this is for a single dipole, so there's no local field effects to worry about. Is this, where P tilde is the charge of the electron times its displacement from the origin. And so that's then equal to E squared over the mass of the electron, omega 0 squared minus omega squared minus I omega gamma, E0 tilde. All right? And so what is the polarizability? Well, there it is. Equals alpha as a function of omega. This is the polarizability. So we've solved it. We've solved the polarizability. And from this, we have then that the ignoring local field effects susceptibility under the Lorentz oscillator model is then just equal to the number density of molecules assumed uniform times, or whatever the local density is, times polarizability, and E squared for m omega 0 squared minus omega 0 squared I omega. And thus, what is the index of refraction? Well, what's the dielectric constant associated with this collection of molecules? Dielectric constant, you'll remember, is 1 plus 4 pi chi. So that's equal to 1 plus 4 pi E squared over m. There's an n here. This quantity up top here is known as the plasma frequency squared. And this is a complex number. It has a real and imaginary part because of this I over here. And the index of refraction is also thus complex. As we're ignoring the magnetic effects. Mu is approximately 1. This is the index of refraction. And that's also complex. All right. So this is an example of a constitutive relationship that gives us the relationship between the response and the material properties. It depends on the nature of the material itself. In this case, we've modeled it, we've narrowed it down just to 2 parameters because we thought about it as a harmonic oscillator that's determined by omega naught and gamma, and of course, in addition, if we then have some density of those molecules, the density determines the mass. All right, so let's take a closer look at this function. Let's since everything's related to alpha, let's look at alpha a little bit more closely. And I'm going to look at that at something a little bit chalk. All right, so my molecular polarizability alpha, we said, is E squared over N omega 0 squared minus omega squared minus I. All right. So let's look at this around near the resonance. Okay, so let's consider response for omega close to omega naught. So let's define delta as the difference between the applied frequency and the resonance frequency. That's sometimes known as the detuning, how tuned away I am from resonance. So omega 0 squared minus omega squared is equal to omega 0 minus omega times omega 0 plus omega, which is equal to minus delta times 2 omega plus delta. We're going to look at, if we're close to resonance, what this means is that delta, the magnitude of delta, is much, much smaller than either omega or omega naught. And I can ignore this. So under that approximation, the polarizability is approximately equal to E squared over M divided by minus delta minus I omega gamma over let's see, somehow I got myself screwed up here. So here's my polarizability. It's a function, remember delta is this difference. Let us write this in terms of real and imaginary parts. This function, by the way, is known as a complex Lorentzian, for reasons I'll remind you of in a moment. We write in terms of real and imaginary parts, we multiply top and bottom by the complex conjugate, and we get minus E squared over M omega naught delta divided by delta squared plus gamma squared over 4 plus I E squared over M delta squared plus gamma squared over 4. Okay? So, what do these functions look like? Let's sketch them. As a function of the difference between the applied frequency and the resonant frequency. How do you sketch a function like this? You don't got Mathematica, which is in the test. You got to sketch it. Well, you look at the limits, right? So for delta small, meaning delta is small compared to gamma, this goes like 1 over delta. Okay? I'm sorry, that's the other way. When it's for delta big, this goes like 1 over delta. When delta is small, I can neglect that, it goes like delta, and I got this minus sign on the front. So what this looks like, the real part, it's linear with a negative slope in the small region, and then it falls off like 1 over delta. Okay? This function, when delta is small, is some constant. That constant is, whatever it is, it's 2 over delta times whatever this thing is. It's got some constant value, it doesn't really matter what it is. And then when delta is really big, it falls off like 1 over delta squared. So it falls off faster than this. And then it goes rapidly up. And then it falls off again. And the full width at half max is equal to gamma. So what I plotted here is the real part of the polarizability and the imaginary part of the polarizability. And this is the famous response function of a damped simple harmonic oscillator. The imaginary part here is a Lorentzian function. So this function here is known as a Lorentzian. All right. So this is why this is called the line width. This is the width of that absorption line. All right, so the question now is, what does it mean for the polarizability to be complex? What is the physical meaning of a complex polarizability? What are the physical meanings of the real part and the imaginary part? Well, let's just go back to the definition. We said that the induced dipole moment as a function of omega was equal to alpha complex E0, right? So that means that the real polarizability, the real dipole moment as a function of time is the real part of this complex amplitude e to the minus I omega t. So let's plug that in. That's the real part of alpha twiddle E0 e to the minus I omega t. Now, we can take this, we can phase shift it any way we like, it doesn't really matter. I mean, I can call this, if I want, E0 times some phase. Let's assume it's linearly polarized. so that E0 is a real vector. So this then says that my induced dipole moment is equal to how do I take the real part of that? Well, let's break alpha up into something which is the real part and the imaginary part. And let's then plug that in and take the real part. When I multiply alpha's twiddle times e to the minus I omega t, what do I get? I get E0 times the real part plus the real part of I times imaginary. Okay? What is the real part of this? Well, the real part is a real number, right? So the real part of this is cosine. The imaginary part is a real number. I times that, what's the real part of that? Sine. So what we find after all is said and done is that the induced dipole moment is equal to the real part of the polarizability times the incident field, which was this, plus the imaginary part, E0 sine omega t. And this is one of the key points. When you drive a harmonic oscillator, and this was the driving field, the phase dependent on the phase of the wave at the position of the charge, then there is a component of the response that is in phase with the drive, exactly in phase, and that is the real part of the response. The real part of this complex function is telling me how much of the oscillation is in phase with the drive. The meaning of the imaginary part is just it's telling me how much of that is in quadrature, meaning 90 degrees out of phase with the response. It's all it means. As we discussed, any function which is oscillating with a certain frequency has a certain amount which is cosine and a certain amount of sine. That's the most general way you can write a function which oscillates with frequency omega. So the real and imaginary parts of the response function tells me how much of that response is in phase and how much is in quadrature.
What do you mean by in quadrature?
It means oscillating 90 degrees out of phase.
I know, but why the term quadrature?
Because we talk about quadrants. 90 degrees. That's an engineering jargon that sticks. So in quadrature means 90 degrees quadrant. Is that how you spell quadrant? I think so. Out of phase. Okay. So, well, okay, so that's a mathematical relationship. It tells us that if I'm driving a linear oscillator, it's going to oscillate with that frequency, and there will be a certain amount that's in phase and a certain amount that's in quadrature. and the real and imaginary parts of the complex response function are those. But physically, what does that mean? What is it? What are the different physical aspects of the part of the response that oscillates in phase and the part that oscillates in quadrature? Well, they have to do with how much work is done on the charge. That's to say how much of the energy is absorbed. So let's look at the issue of absorption. So when we want to talk about absorption, we want to ask the question, how much work do the fields do on the charges? Well, the rate at which work is done on the charges is given by the local velocity of that charge dotted into the force that's acting due to the fields. That's power. In our case, the force is given by the minus the electric charge. Electron charge is minus E times the local electric field. So this is equal to minus P dot into the electric field. No, it is just equal to P times that. E picture, right? So now we can plug this in. Let's look at the case. Now we can do this quickly and easily. Let's look at the case. Let's look at as I time average this, time average over a period of oscillation. That's the time average of this. And we know how to quickly take the time average of a product of functions which are oscillating at a frequency, omega. How do we take that time average?
Complex conjugate.
Sorry?
Complex conjugate.
We use the complex amplitudes and the complex conjugate. So first of all, we have to express this in terms of the complex amplitudes. So P dot is the real part of minus I omega P twiddle, e to the minus of omega t. So this is the complex amplitude of P dot. And E is the real part of E naught twiddle, e to the minus I omega t. This is the complex amplitude of E. Sorry, no omega naught, it's omega. So the time average then is 1/2 the real part of the complex conjugate of one of these guys dotted into the other. Okay? So now we can plug that in. We got omega over 2. We got the real part of I, P twiddle star, dotted into E naught. Okay. So, what we find then is that the time average rate at which work is done on the charges is equal to omega over 2 times the real part of I alpha star plugging in P with alpha E. So this is then equal to times the real part of that. What is the real part of I times alpha twiddle star? It's the imaginary part, right? If I write this is the real part of alpha minus I times the imaginary part of alpha. Thus, when you multiply by I, what you get is, as promised, the amount of absorption I get is related to, it's proportional to the imaginary part of alpha. And it's proportional, of course, to the energy that's being put in there as well. So, why is that? What's going on? Why does the in quadrature part of the response have anything to do with absorption? Well, as we've discussed many times now, the work that's done on the charges depends on how the current is flowing relative to the electric field. So remember that we have the ohmic heating was J dot E. That's the rate at which I do work per unit volume, right? It's the same thing that we just wrote down there if I just divide this. Why is that? Because in this case, what is J? J is the polarization current, right? It's the current due to the oscillating polarization. And we discussed that was the derivative of the polarization with respect to time. Okay? So, if this oscillates like cosine omega t, then the part on time average, which gives rise to heating, well, this has to go like sine. So when you take the derivative, you get back cosine. Otherwise, on average, there's no energy absorbed. So the amount of work that's done on the charges depends on the response being in quadrature. And that's the meaning of the imaginary part. Okay, very good then. What about the real part? Well, this generally gives rise to what's called dispersion. If there is a reasonably strong frequency dependence in the polarizability. Why is that? Well, we can look now at the index of refraction, which we said was the square root of 1 plus 4 pi n alpha. Okay. And if this were real, well, then this would be real. And we have then that each plane wave travels with phase velocity that is given by the real part of the index of refraction, which generally depends on omega. In this way, we see the dispersive line shape. That's what this function is often called. So back to Lorentzian here, let's just quickly discuss. We just said here that the amount of absorption that we get of energy into the oscillator depends on the imaginary part of the response. So the amount of amplitude or amount of energy absorbed is biggest right on resonance and then falls off away from resonance. and the strength of the resonance or the width of the resonance depends on gamma. So if I'm way off resonance, I don't absorb very much energy. The other function here has to do with what we call dispersion, and it's called the dispersive line shape. Okay, so what if we have now a polychromatic pulse, which is a physical pulse. You can't have a single frequency forever, that would go on forever, but that means that we have a spread in frequencies and not a spread in phase velocities, which leads to dispersion. And that's what I want to finish our discussion with. Okay, so let's consider the following problem. Let's say I have a microwave horn that I hook up to some signal generator, and it sends out microwaves, electromagnetic waves, into a medium that is, I'll just take it to be semi-infinite. Okay? So this is a dispersive medium. And I'll take it off, I'll say I'm way outside any absorption band, but there's still some index of refraction that's a function of omega. And I want to know how I send in some pulse, which is determined by some generator that makes some electric field that does something as a function of time. And then it propagates into the medium. And I want to solve for what that pulse propagation is. So I'm just going to ignore, there's just going to be a single polarization, so I'm not going to take into account the vector nature. I'm just going to say this is the amplitude. And this is the real signal. Okay? And let's call this the z direction, and this is z equals 0. So right at z equals 0, as a function of time, is some signal. Okay? Which we can decompose in terms of its Fourier components, according to the Fourier transform. And recall that we can break this up into the integral over the positive frequencies and an integral over the negative frequencies. Just breaking up the integral. This is what has the very creative name, the positive frequency component and the negative frequency component. No hat on this. I'm thinking about quantum. Not quantum. Okay? And you will also recall that if this is a real field, that the Fourier transform satisfies that when I take the conjugate, I just said omega equal to minus omega. And that means from that this is equal to the positive frequency component, the conjugate of that. So my field my signal as a function of time is twice the real part of the positive frequency component. Something plus its complex conjugate is twice the real part of that something. All right, so that's the input signal. What is the signal if I had an antenna, a microwave antenna down here, somewhere downstream? I want to know what is the electric field as a function of time at some position z. The signal, of course, propagates inside this medium. So, we can write that down instantly. E plus as a function of z downstream, well, each frequency component propagates with this phase velocity. So the positive frequency component at a later time, downstream at a bigger z is equal to end of story, and we've solved it. What it's saying is that the signal for a given frequency component that I see at my position depended upon what the antenna was doing at an earlier time. The time it takes that phase to propagate, if it's oscillating at that frequency, down to my position z. Is that clear? Okay, this is what's known as the retarded time. What I see now depends what happened in the past. All right. So now we just have to do this inverse Fourier transform, and we've solved the problem. Let's look at it for a specific case, the case where I'm going to think about a quasi monochromatic, not monochromatic, but quasi-monochromatic. And as we discussed, what we're talking about is a pulse of a certain duration with whatever shape it has, and it's got lots and lots and lots of oscillations, where the period of oscillation t is tiny compared to the duration of the pulse. Okay? That's a quasi-monochromatic pulse. So this is my E as a function of time that's being spit out of my antenna, my source, my microwave horn. So it's got some envelope that's modulating this carrier wave. Let's take the carrier wave to have a phase of 0 at time t equals 0. Okay, so this is t equals 0. So the envelope function is this dotted thing. As we discussed earlier in the previous lecture, the Fourier transform of this is just given by, I don't know if that was my pocket or yours, but anyway. It's given by 1/2 the Fourier transform of the envelope function centered at frequency omega naught and at minus omega naught. So T tilde is the Fourier transform of the envelope function. Remember that? We talked about this a few lectures back. So if I were to sketch this Fourier transform it would have one peak centered at positive frequency omega naught and one peak centered at minus omega naught, with a width which is narrow compared to omega naught under the assumption of monochromaticity. Okay, so delta omega is the width of this peak, which goes like 1 over the duration of the pulse, according to Fourier duality. And the assumption is that this width is tiny compared to that. That's to say, this width is tiny compared to that distance. So, with that said, we can write down the solution for this particular form of my signal. The positive frequency component then, input is equal to 1/2 0 to infinity d tilde centered. I don't mean not. Plugging in. However, this function has negligible coverage in the positive part of the axis. So this is negligible if it's quasi-monochromatic. Right? Moreover, this thing, its tail is 0, essentially 0 in the negative plane. So this is approximately equal to minus infinity to infinity to factor out that half. And thus, the positive frequency component at position Z, to good approximation, if it's quasi-monochromatic, is 1/2 minus infinity to infinity e tilde minus omega naught, omega t minus z over the group velocity. I'm sorry, the phase velocity. We'll get to the group velocity. Damn, we're not going to get to it today. Integrated over omega. And of course, this is omega over the phase velocity is equal to the wave number. So that's e to the I k as a function of omega z minus omega t, where k as a function of omega is equal to omega over the phase velocity, which is omega over c times the index of refraction. If this were complex, this would still be true. We would just put in tilde over there. Okay? Let me just spend 2 more minutes on this, because it'll be a much more natural breaking point for us. Let's define, as we did before, this as delta. It's the difference between the frequency and some central frequency. Then we can rewrite this as equal to 1/2 the Fourier transform as a function of delta e to the e to the I k omega naught plus delta as a function of omega naught plus delta times z minus I delta t minus I omega t. Okay? Just writing omega is equal to delta plus omega naught. Okay, so now we make an important approximation. This function has narrow support. We're integrating over all delta, but it only has its support for delta close to 0. So that means we can look at this function only near where delta is 0, because this function is peaked only near delta equals 0, and then it falls off extremely rapidly. So we can, for a quasi-monochromatic pulse, we can Taylor series expand our function k as a function of omega is approximately k at the central frequency, omega naught, plus delta times the derivative of k with respect to omega at omega naught, plus a half delta squared, the second derivative, etc. So if we just take the first order term there in delta, this is approximately equal to 1 over 2 minus turning to infinity d delta 2 pi integrating over all delta. But this is only peaked near delta equals 0. E to the minus I delta t minus z d omega dk at omega 0 times e to the I k at omega naught z minus omega naught t. And thus, we see that if we recall, we have the phase velocity was defined as omega over k. We define the group velocity as the derivative of omega with respect to k, which is generally different if we have a nonlinear dispersion relation. This is equal to 1 over the group velocity at that frequency. And this is nothing more than the inverse Fourier transform evaluated at this point. And so we end up with the following final answer, which we will analyze. This pulse moves. Its center moves at the group velocity. The carrier wave propagates. The phase propagates at the phase velocity. We'll remind ourselves about that some more next week.